Hello there. Welcome to our today's science lesson. Our topic for the day being particles in elements and in compounds. Now, as you already know from our previous topic, we were talking about matter, which was in three states, that is gas, liquid, and solids. And in any of those three states, we discovered that we have small particles in that state. The small particles are the ones that form that state, which is matter. Now, in today's topic, we want to look at those particles, but in a different way of description, that is particles in elements and compounds. So we are introducing two new words here, elements and compounds. But these two words are not that new. In other topics you covered in the previous year, you also mentioned some of these things in one way or another. So, before we cover so much about elements and compounds and the particles that form those elements and compounds, we need to review in a way to remember or see how much we can remember or how much we know about the same things from the previous topics. Some of the issues we can look at are like symbols of elements, molecules, symbols of molecules, some uses of these elements and molecules, probably where they are found, who was involved in getting to know maybe the symbols or the elements and how they can be used, and so on. So I will be giving, I'm going to give out some of questions as statements, whereby we shall be looking at it in a little bit more detail to know maybe probably the symbol of the element or the use or where it is found. Number one is, what is an atom? What is an atom? You remember in our previous topic we talked about a scientist, Democritus, who was the first scientist I mentioned when we were talking about kinetic theory of matter. This scientist is the one who discovered that matter is made up of very tiny small particles, and these tiny particles are the ones that determine the state of matter depending on the energy they are having. So these small particles, in our today's lesson, we are going to look at them and give them a name as an atom. So the question is, what is an atom? And an atom is the smallest particle of an element that can take part in a chemical reaction. We are adding here now a statement, chemical reaction. You can look around and you discover that most of the reactions we are having, we even don't understand how it happens the way it happens. But having understood what is an atom and what is an element and later on what is a compound, we shall be able now to understand some of the things that happen around as reactions, but we don't know why they happen the way they do. So an atom is the smallest particle of an element that can take part in a chemical reaction. In that chemical reaction, it can be in a gas state, liquid state, or solid state. That one does not matter so much. What matters is the smallest particle, in this case, is an atom. We can also look at it in terms of a formula. If you have something like water, which we talked about so much in detail, water. What is a liquid? It can be in gas form. It can be in solid form. How do we write water as a symbol in chemistry? Water. Water is written as capital H to then capital O. H and O must be of the same size, and they must also be written in capital form. So you don't just look at the size, but you look at the shape of the letter and the size of the letter. If the letter is one of the two letters appears smaller, then it will be interpreted as a small letter. So you don't just look at the size, but you look at the size and the shape. Now, this is water as a chemical symbol. What does this one mean? This one means that we have 3 atoms that have come together. 3 atoms, smallest particles of an element that can take part in a chemical reaction. So the chemical reaction that took place was to make water as a molecule. And the atoms here are hydrogen, which is written as capital H. And in this formula, we have 2 atoms. Then we also have oxygen, which is written as capital O, where we have only 1 atom. Now these 2 atoms of hydrogen and the 1 atom of oxygen, when combined, they now give us water. They combine in a chemical reaction, just as we are as we have defined what is an atom as the smallest particle of an element that can take part in a chemical reaction. So these 2 hydrogens and this 1 atom of oxygen can only combine in what we can call a chemical reaction. Now these hydrogen 2 atoms do not exist as an atom in a natural setting. They will exist in a different form. And this one brings us to another thing, a molecule. So we have another small particle by the name a molecule. A molecule is different from an atom in the sense that a molecule will have 2 or more atoms together. 2 or more atoms together. Why the 2 or more together is they make them to be able to exist in a natural condition, natural setting. So atoms together existing in a natural setting, we shall call them a molecule. For this water to be written this way, and it is comfortable to exist naturally, then we can say this is a molecule of water, which gives us the smallest particle of water as a molecule, naturally existing under normal conditions, a molecule. But this molecule is made up of atoms, and these atoms are hydrogen atoms and oxygen atom. But as we have just said, these atoms do not exist naturally as atoms. They will exist as molecules. So for hydrogen, it will exist as hydrogen gas. Hydrogen gas. For oxygen, it will exist as oxygen gas. As you can see, we are seeing 2 hydrogen atoms coming together to form 1 particle by the name hydrogen molecule. 2 atoms of oxygen coming together to form 1 particle by the name oxygen molecule. So for these 2 to combine, it will be in a chemical reaction that we can call combustion. Hydrogen can combine with oxygen in a combustion reaction now to form water. So the chemical reaction here will be combustion, where hydrogen gas will burn in oxygen to give water as a product, which is now our molecule here with the formula H2O. We can also look at other symbols, like we shall just pick common formulas that you have been encountering, like this. This is sulfuric 6 acid. It can also be called sulfuric acid, but looking at the oxidation number of sulfur, we can call it sulfuric 6 acid. That's based on the oxidation number of sulfur, but you can generally call it sulfuric acid. Now these are common substances we encounter in our life. If you have a machine like a vehicle, you have that battery that powers the vehicle for the engine to start. Looking at the liquid found inside, this is the liquid, sulfuric acid. Sulfuric acid, the formula here, you have to be careful. Hydrogen standing for a different element, sulfur standing for another different element, and O also standing for a different element by the name oxygen. All must be in capital form when being written, by size and by shape. The 2 here means 2 hydrogen atoms are required in this formula and 4 oxygen atoms are required in the formula. The other common acid we always encounter is hydrochloric acid. Very common, you even have it in your stomach, very helpful in our stomach. It makes the acidic condition, which is very, very important in digesting some of the foods we eat in the stomach, to take place. We also have it in so many other reactions, as we shall be encountering them as we move on with our science lessons, particularly in the chemistry side. How to write the formula? This is how it is done. Now, I've picked on this one because of the problem associated with L. When writing the formula of chlorine, you need to know that the first letter must be a capital letter, which is capital letter C. The second letter becomes a small letter. Now, when writing a small letter, some make a mistake of writing L with a slight bend. Once it is done this way, it is wrong, because this one is interpreted as a capital letter L. It is similar to this, even if they don't look so much alike, but they are taken to be the same. Since you have made the second letter a capital letter, it will have gone against the rules of writing chemical symbols. So this one becomes wrong. The correct way to do it is, when writing L in any symbol, use just like writing 1, no bend. So that's why I picked on this one, so that you can look at such. Another symbol we can look at is aluminium. Aluminium as a metal. These are very common metal we encounter in so many cases. It is used in making so many of the bodies like planes. Aluminium is strong but light, so it is very comfortable when used as a material in constructing planes. It can also be used in areas that you expect to resist water, because it does not easily get corroded. It forms a coating on top which prevents it from corrosion. So how do we write this metal aluminium? Aluminium is capital letter A, small letter L. The same, the L is just 1. The other substance we can look at is silver. Silver is also a metal, a precious metal. You have heard of people who have been involved in competitions. When you get a silver, you really smile, showing that you have done something what the others didn't manage to do. Then how do we write it as a formula? Silver is capital letter A, small letter G. Now this G, you have to be careful. There are those who can do a mistake of, when bending this, you make this mistake. The 2 letters have come into contact. Once this one happens, you have interfered with the normal interpretation as in English. This A in English will appear capital letter A, and G will appear as a small letter G. But in chemistry or in science, once it happens this way, it changes the meaning for A. When they are in touch, then this one is taken to be a small letter A. So make sure when you are writing your chemical symbols, letters do not touch each other. The other compound that is common with us is carbon dioxide, which is also called carbon 4 oxide, based on IUPAC way of naming. Carbon dioxide, carbon di, so CO2, di means 2, so we have 2 oxygens and 1 carbon. The same to this, there's a common mistake people make of writing carbon 4 oxide or dioxide that way, whereby the first letter C is written as a capital letter, but the second letter, which is oxygen, is written as a small letter. This one only happens when these 2 letters mean the same thing. For example, the case of chlorine, I can also add there sodium, where the 2 letters stand for the same thing. N and A all stand for sodium, but here C and O do not stand for the same thing. C means carbon, O means oxygen. Since the 2 are totally different, then they must all be represented by a capital letter by shape and by size. If written this way, then this one will mean cobalt. Cobalt is where you will have the first letter is capital letter C and the second letter is O, but a small o, small letter O. This is cobalt. So looking at it and this one, you get it confused. You can also look at it as carbon 2 oxide or carbon monoxide, the poisonous gas that can easily kill you when you have a burning flame, jiko, or the vehicle engine is on in an enclosure. You can easily collapse and die because you are breathing in carbon monoxide, or what we also call carbon 2 oxide. That's the oxidation number of carbon. Now in this one, just like in carbon 4 oxide, the C is for carbon and O is for oxygen. Since there are 2 different elements, then they have to be represented by 2 different letters of same size and by shape also appear capital. This is carbon 2 oxide, but this is cobalt. You mess up with the size, you see now you'll have interfered with the whatever you are talking about. You'll have caused a confusion whether you mean either cobalt or carbon 2 oxide or carbon 4 oxide. Since we are also talking about elements and compounds, we also need to understand things like what is a mixture? What is a pure substance? What is an impure substance? This is prior knowledge we need to know so that you can be able to understand this. So let's start with a mixture. A mixture, this is a common thing you did since you are a small child. You are mixing up things. So what is a mixture? A mixture is a combination of 2 or more substances that you can easily separate physically. For example, I can say this and this are 2 different things. If I put them together, I can say I have a mixture of mark pens and an eraser. If I want to separate these, I can do it very easily and physically by just hand picking. I have separated. Then whatever I had was a mixture. But if you find that you are putting 2 or more things together, and when it comes to the point of separating, it becomes hard. you require a higher mechanism, that is chemical way to separate the two, then that ceases to be a mixture, it becomes something else, and that is a compound. So a mixture and a compound have one thing in common. They have two or more substances that were originally different, but that have been put together to form one thing. But the two are also different. For a mixture, the separation can be done physically, but for a compound, the separation can only be done one way, using chemical means. Mixture, physical means, a compound, chemical means. Then, what's a pure substance then? A pure substance is an accumulation of small particles of one particular type. Accumulation of small particles, but of one particular substance. And the one particular substance here is the smallest particle that is forming that substance, which now in our topic, and which was also seen by our scientist Democritus, who said matter is made up of small tiny substances called an atom. So when you talk about a pure substance, this is a substance that contains one particular type of atoms, or those atoms have come together. They can be of the same type or different type. So different atoms have come together and they have formed another smaller particle that you cannot be able to separate physically. For example, you have formed something like a molecule. A molecule is also a small particle, but a little bit bigger than an atom, because a molecule can be made from atoms. But this molecule cannot easily be separated by physical means. You cannot. So in that case, whatever a molecule will form can also be called a substance. And that substance can later on be called a pure substance of that particular type of material. For example, water. When you look at water, water is a substance. But this water is made up of molecules. And the molecules are made up of atoms that were chemically combined. And the atoms were hydrogen atoms plus oxygen atoms. So a pure substance can be made of either same type of small particles by the name atoms, or small particles of the name molecule that have been formed from either the same type of atoms or different types of atoms, but you have made a small particle that cannot be separated or cannot be broken physically, but it can be done chemically, because you can break this water into hydrogen and oxygen using chemical means. We can also look at what is a compound. Though I've already mentioned that a compound when I was talking about a mixture, but you can see a compound is a combination of two or more pure substances. We have understood what is now a pure substance. It can be same type of atoms or same type of molecules. But now we are talking about a compound. What is a compound? A compound comes in to be a combination of now these atoms together to form that substance that you cannot be able to separate physically. For example, this molecule is now a compound. Why? Because you combined two things that are totally different to come up with another new thing that you cannot separate or take back to the original physically, and that is water, a molecule. So since you have formed this new substance that you can now no longer take back to hydrogen and oxygen physically, then this one qualifies to be a compound. A compound can also be formed from bigger particles like molecules. I can have a molecule like water reacting or combining with another molecule. For example, I can have it like I have common table salt, sodium chloride. When you combine these two, you will form a solution. This is a solid crystals and this is a liquid, that's a solvent. It will give us sodium chloride, but a solution. Now, this one is in a state of confusion to some, because some can easily say, I can still get back my sodium chloride from sodium chloride solution by just heating to evaporate. True. But that process of heating to evaporate is not just a physical process. It's both physical and chemical. Because when you talk about a chemical process, this is a process where energy is involved. And when you are heating, indeed, you are supplying energy into the system. So for you to get back your sodium chloride crystals, which is a common table salt, you will have to evaporate this. As you evaporate, you will have to make sure that you condense the steam you will have lost, which was having more energy, as we saw in the kinetic theory of matter. More energy, but when it will meet a cold surface, it will have to be cooled, then it condenses back to a liquid. Your water will have been gotten back. But the whole process of getting this and this back is involving heat energy. So this one can be taken as a chemical process. But we can also look at another one, a compound, where maybe you have a compound like sodium hydroxide, which is an alkaline solution, a basic solution. I can react it with our common acid with us, which I mentioned, it is found in our stomach, that is hydrochloric acid. When these two meet in a reaction, they will form sodium chloride, what we have just talked about up here, then plus water. We have formed two different substances from our acid and our alkaline or basic solution. Can we be able to go back? The answer is no. You cannot do it, at least physically. So since you cannot take back the sodium chloride to hydrochloric acid or sodium chloride to sodium hydroxide, then what we have formed here is a compound. So we have used a compound plus another compound to form another compound. You can still use atoms plus another atom to form a compound. So therefore, a compound is a combination of either atoms of the same or different types of atoms to form a substance that you cannot separate physically, or a combination of other smaller compounds to form another new substance which you cannot separate or break or reverse to the original reagents. That is different from a mixture, as we had done the comparison of a mixture and a compound. We also need to understand things to do with the gases. These are things we learned in our previous years. Gases. We have different types of gases, and we need to understand some information about these gases and how they exist, so that when it will come to gases in relation to compounds and from which elements, it becomes easier. So in gases, we have to understand terms like monoatomic, diatomic, triatomic, and such. In our level of study, these are the three common ones. In our level of study, these are our three common terms we need to know or understand so that we can be able to explain why some of the gases are the way they are. When you talk about a monoatomic gas, these are gases or these are substances that exist in gas form, gas state, gaseous state. But when you look at them, you find it is just a single atom. So many atoms have come together, but they are existing as a gas. This one only exists for those elements that do not react. Elements that do not react. So when they do not react, they will naturally exist just as single as they are. Such elements are the ones we call noble gases. For example, helium, neon. Looking at these two gases, these are gases that you will never see any other number apart from 1 written anywhere. Why? Because the atoms of helium or the atoms of neon exist on their own as one. Mono means one. So they exist as one. And since they are existing as one, but in a state of gaseous, then we call them monoatomic gases. These are noble gases. Then we also have diatomic. Di meaning two. So these are gases that have two atoms together to form one molecule. A good example is oxygen gas, which is written this way, meaning that two oxygen atoms have come together to form one oxygen molecule. So that molecule, which is having two atoms, will be called diatomic, meaning two atoms together to exist naturally. Another example, here we have so many of them. Nitrogen gas is another good example of a diatomic gas. You can also get diatomic gases of different types of atoms. So being di does not mean the atoms must be of the same element. They can as well be of different elements. An example here is carbon monoxide. Carbon monoxide is a gas. Looking at it, these are two atoms. One atom of carbon, another atom of oxygen. Since these are two atoms and this is a gas, so it can also be called a diatomic gas. Though we commonly talk about diatomic gases in respect to those gases that have atoms of the same element, but it also applies to atoms of different elements. The third one is triatomic gases. Here we have gases that have three atoms forming one molecule. A good example of a triatomic gas where you have one type of atom but three of them is ozone. Ozone is three oxygen atoms together. It is the famous ozone that you have once heard of it, which is forming a layer in the atmosphere, which is very important to us because it protects us against the harmful rays from the sun. So that layer is made up of oxygen atoms, but it does not form oxygen gas as it is here, nor does it form oxygen, or is it oxygen atom as an atom? No, it's not an oxygen atom, neither is it oxygen molecule. It is called ozone, and this is the formula. 3 oxygen atoms together to form one molecule by the name ozone. We can also have a triatomic gas that comes from different atoms together. A good example is our carbon dioxide or carbon 4 oxide, where you can see 1 carbon atom and 2 oxygen atoms together to form one molecule, which is carbon 4 oxide. So what we are talking about here is atomicity of gases, which is important to be understood before we proceed with our topic, because in one way or another we shall have to go through all of this. We also need to understand the periodic table. We also need to understand the periodic table. And to understand the periodic table, we have to get some basics of the same table. And the basics of the periodic table is to know that elements that are found in the periodic table can be categorized into groups based on the properties or behavior of the elements that are placed in the periodic table. So the periodic table can be put into 2 major categories, and that is metals and nonmetals. Metals and nonmetals. When do we call a metal, an element a metal, and when do we call an element an nonmetal? This comes from the properties the element will be giving. However, the best way you can go about this will be looking at the electronic configuration of that element. These are things you covered in the previous science lessons on how you can write the electronic configuration of an element. An electronic configuration comes from the number. An electronic configuration comes from the number of electrons an atom carries. So if we have an element A, which is having 6 electrons, then how do we write our electronic configuration? We have to follow rules, and the rules are: the first energy level carries 2 electrons. The second energy level can carry a maximum of 8. But out of what we have been given, this element A is having 6 electrons. So out of the 6, we have already gotten out 2. How many are we remaining with? 4. So since 4 is less than 8, we have the 4, the whole of it, as our second electronic energy level when writing the electronic configuration. Out of these, we can easily be able to identify metals and nonmetals, apart from physically looking at the properties or the behavior, the element or the substance that has been made from those elements is showing. Now, let's look at an example of 8 elements. Try to write the electronic configuration, and out of that, see if we can be able to identify metals and nonmetals. So let's assume we have elements A, B, C, D, E, these are 5, F, 6, G, H. 1, 2, 3, 4, 5, 6, 7, 8, 10 of them. So we have this one has 1 electron, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. The electronic configuration must follow rules. And the rule number 1 is the first energy level must have a maximum of 2 electrons. The second energy level must have a maximum of 8 electrons. If that is the case, which electronic configuration are we going to get out of all of this? For the first one, maximum is 2. It only has 1. So that's the only one that we shall have. So it will give us electronic configuration as 1. The second one has 2. Maximum 2. So by writing 2, we have nothing left. So it remains that way. The third one has 3. Maximum for first energy level is 2. If we write 2, 1 is remaining. That 1 is the one we shall take to the next energy level, and that is 1. So it gives us an electronic configuration of 2, 1. We can do the same for all this, and we get it as 2, 2, total 4. 2, 3, total 5. 2, 4, total 6. 2, 5, total 7. 2, 6, total 8. 2, 7, total 9. And 2, 8, total 10. So these are the electronic configuration of these elements. Out of the electronic configuration, we can be able to identify metals and nonmetals by looking at the number in the outermost energy level. The ones that are outside are the ones we call outermost energy levels. Any that will have 3 and less will be categorized as a metal. So 3 is here. So you can say A, B, C, D, E are metals, and F, G, H, I, J are non-metals. But it is always not true for all elements or substances, because we also have, in addition to the electronic configuration, the physical behavior of the element. And in this case, I want us to look at these two elements, A and B. This one has electronic configuration 1. Outermost is the same as the innermost, which is 1. So A and C seem to be the same because they all carry 1 in the outermost. But you will discover that the physical behaviors, characteristics, A will give, some will be agreeing with the C, but some will not. And if you look at the periodic table, A is hydrogen. So you'll find that in the periodic table, some will place hydrogen at the center, not in any of the groups, as we shall study the periodic table later. Reason being, hydrogen gives mixed characteristics. It gives some characteristics of metals. Metals are on the left of the periodic table, and at some time it gives characteristics of nonmetals, which are on the right. Because of that, it's placed at the center. So you don't just look at the electronic configuration, you also look at some of the characteristics it gives. The other one is B. And in the periodic table, this one is helium. Helium has 2 electrons. So you cannot just use 2, just like D, which has 2, and say, since D has been taken to be a metal, therefore B must also be a metal. No. Looking at the physical characteristics helium gives, it gives characteristics of nonmetals. So it can also be put in that category. However, elements that have their outermost energy level full, as much as they can be taken as nonmetals, but those are special nonmetals. These are nonmetals that do not react, and therefore the correct way to describe them are noble gases, and that is B and J. Outermost energy level, first energy level is 2 electrons. Outermost energy level for the second energy level is 8. So J and B have their outermost energy level full, and therefore the best way to describe them is noble gases. So elements can be categorized into metals and nonmetals. Examples of metals are like sodium, magnesium, potassium, calcium, and examples of nonmetals are like oxygen, sulfur, phosphorus, silicon, and so on. Further division can also be done on the periodic table with further analysis, where you will find some nonmetals being put in a special zone of metalloids, semi-metals, like silicon. This is a substance that can be used as both a conductor and an unconductor. But that is an area we have to learn in a much deeper manner in a different topic. But for now, we have metals and nonmetals, and examples are the ones as I've given: sulfur, phosphorus, silicon for nonmetals, sodium, potassium, calcium for metals. But you need also to understand that the periodic table is made up of so many elements, around 118 elements, 92 of them being physically present. You can find them, but the others are found only when we have radioactive decay. They exist for a very short period, but even if it's for a short period, they are there. So giving a total of 118 elements in the periodic table. Out of all those, we have metals and nonmetals. From what we have been covering, we have seen that there are so many aspects that we need to remind ourselves, which may come from various topics you have been covering since you started covering science, and in one way or another they will be very helpful as we proceed on with our lesson. Just an overview of what you have covered today. Give me the symbols of the following: copper, as a metal; iron, as a metal; now you realize that the symbol you have given does not always agree with the name of the element or the substance you are talking about. The formula for copper is Cu, where C is a capital letter and U is a small letter. For iron is Fe. Now, of the two, you can see this one is at least a bit closer to the name, though the name is starting with the CO, copper. But that does not give us a direct expression that should be the symbol. So the symbol comes from other names that were given before the real name came in. And the name here is cuprate. Cuprate was the original name that was used, which was the one that gave the simple Cu, cuprate. And for iron, as you can see, it is not even an I or an R, it is F and E, which comes from the word ferric or ferrous. So iron can also be described as a ferrous material, and that's where the letter Fe comes from. This one is only to show you that when writing simples, remember the following. 1. Letters should not touch each other. 2. Letters standing in for different elements must always be capital by shape and capital by size. 3. The formulae of the element or the compound must not always take the letters from the name, like for the case of sulfur. If you look at sulfur, the symbol is S. Sulfur S, sulfur S. So it is not always the case. It has to go with the original name that was used when identifying the letters. You also need to realize that elements exist both in the 3 states of matter. There are those that exist as gases, those that exist as liquids, and those that exist as solids at room temperature. Liquids are like mercury. And lastly, you also need to remember that these elements we have been talking about as elements or as molecules, the product of the elements when they combine to form the compounds, have different uses. And the use will always come from the properties of the element or the molecule that has been formed. In our next lesson, we shall be looking at how various elements came into existence, how were they discovered, who discovered those elements, and their uses in relation to what we have been covering today. Thank you.